Swayam Prabha. Digital India. Educated India.
Hello everyone. Today I am giving a lecture number 3 of module 2. Based on the formulations developed in my earlier lecture on simply supported rectangular plate, I will go further to take up some problem which are frequently encountered in our practical application. So, today what I want to discuss is analysis of simply supported plate resting on elastic foundation, that will be my first topic. Then I will go to analysis of equilateral triangular plate subject to edge moment, and we will see how some other exercises based on Navier's method that we continuing till today can be solved. So, simply supported plate that I have discussed is best possible way to find the solution is taking a double trigonometric series, and it gives you the exact results, because it satisfies the geometrical as well as force boundary condition on the edges, and therefore, it is possible to get the exact solution for the deflection surface. Once the deflection surface is obtained, one can find the bending moment in two directions x and y, twisting moment m x y, S shear force V x and V y, and shear force also at any point q x and q y, as well as your this corner reaction, that is very important in case of simply supported plate where the corners are not restrained, because in that case corners have a tendency to lift up. Then these elastic foundations are actually the material which offers the resistance to the deflection, just like it acts like a spring. So, when a plate is resting on a spring, the spring is uniformly distributed over the area, it is not at the discrete point. So, naturally the load acting on the plate will be reduced by the spring forces, the upward spring forces. So, that has to be taken into account to modify the governing differential equation of the plate. The most important parameter for such type of problem, that is problem number 1, simply supported plate on elastic foundation, is the value of the subgrade modulus of reaction. That value is sometimes very difficult to find out accurately. The example of such type of problem is found in case of foundation design. So, when we consider a foundation slab resting on the soil, that soils offers a upward reactions, that is soil pressure is distributed over the plate area, and in that case the subgrade modulus of soil is very important to be given as a input to the problem, otherwise our analysis will be wrong. And subgrade modulus in case of soil generally is found by plate load test, and the value that we take from geotechnical engineer we will use for our analysis in structural component. Okay. Then we have a type of plate which is triangular in shape, and I have idealized this as a equilateral triangle, because such type of plate is slab is also or plate is also common. It is not necessary that always the plate should be rectangular, but most common application is rectangular and circular, but sometimes other than rectangular and circular other shapes are also adopted in practical application. So, one problem I have selected or that triangular plate, equilateral triangular plate subjected to edge moment of equal amount, equal magnitude acting along the edge uniformly distributed. So, that problem we will see, and later on two exercises I will discuss, and I will give important steps to find out the solution for that exercises. Okay. Now, let us see this plate, which you can see a rectangular plate, the length is A and the breadth is B. The load acting on the plate is q x y. It may be uniformly distributed load, or it may be concentrated load, or any other type of load, uniformly varying load. So many cases may arise, and it is resting on the soil subgrade or elastic subgrade, that is we call the elastic foundation, which is model as a spring, that is called Winkler foundation model. So, spring is representing the soil here or elastic subgrade, which offers upward reaction to the deflection of the plate. So, at any point on the plate, the spring force will be the modulus of subgrade reaction if the value is k, and the deflection at that point k into W will be the upward spring force, and that force will reduce the loading, that is downward load, that is applied on the plate. So, net loading will be q minus k into W. Okay. So, you have seen that due to reduction of the net loading q minus k into W, we can write the differential equation in modified form. D is the flexural rigidity of the plate, which is equal to E h cube divided by 12 into 1 minus mu square, where mu is the Poisson ratio of the plate, and d del 4 W equal to q minus k W. So, right hand side of the equation is now modified. If you see the ordinary plate equation where no elastic foundation is there, then k can be put to 0. Then the equation of the plate becomes d into del 4 W equal to q, where del 4 W after expansion we can write it as a del 4 W del x 4 plus 2 del 4 W del x square del y square plus del 4 W by del y to the power 4. Okay. So, this biharmonic operator I have explained you earlier, and after expanding we can write this differential equation with all the terms. Okay. So, thus del 4 W is equal to k by d into W equal to q x y into divided by d. Now, here one thing you should note that the thickness of the plate is uniform throughout the area, and also the soil stiffness, that is the subgrade modulus, is also constant, but in some problem it may vary also, then the k will be a function of the x and y. So, similarly, if the thickness is varying with the space variable x and y, then you will get this d as a variable in the differential equation. Now, let us consider the boundary condition as simply supported. Now, simply supported boundary condition, why I am discussing? Because we have already formulated this problem and we will apply this to rectangular plate resting on elastic foundation. But it is also true that except the simply supported boundary condition, other boundary conditions are also available in the practice. For example, if I consider the foundation which is acted on by column load and by this upward soil pressure, then I can treat this the foundation is fixed at the edge of the column and the edges of the foundations may be taken as free. So, in that case boundary condition will be different. Okay. Now, let us see the boundary condition in that case is our simply supported boundary condition. So, we will see that the curvature along x direction is 0, along x is equal to 0 and x is equal to a. Deflection is 0 of course, because it is supported, and here again y is equal to 0, y is equal to b, deflection is 0 and curvature in y direction is 0, because it is supported along y direction. So, the curvature along x direction, you can see that plate where y is equal to 0 edge is y is equal to 0 edge means it is parallel to x axis. Okay. So, if it is parallel to x axis, then there cannot be any curvature along the x axis. So, the curvature term with respect to x is omitted here. Similarly, here also you can see this condition. Now, according to Navier, we assume a double trigonometric series, because this series satisfies the differential equation completely and boundary conditions fully. So, depending on the value of AMN, the correct value of W or deflection surface can be obtained. Okay. So, AMN into sin m pi x by A into sin n pi y by B, where m and n are integers, and you have noted that in the my first lecture, while I discussing the simply supported conditions of a rectangular plate, deflection is composed of so many waves, half waves in x direction and y direction. So, deflection surface is composed of half waves in x as well as y directions. Okay. Now, substitute 2 in equation 1. Equation 1 is our this differential equation. Okay. This equation is 1. So, if I substitute this in the differential equation, then equation 1 can be rewritten as this. Okay. And after substitution, you will get this term, that is after fourth derivative, you can see m to the power 4 pi to the power 4 divided by a to the power 4, this term will come, and for fourth derivative with respect to y, again n to the power 4 pi to the power 4 b to the power 4 terms will come, and the middle term, that is the cross derivative twice with respect to x and twice with respect to y, then you will find that m square n square pi to the power 4 divided by a square b square term will come, and since it is multiplied by 2, we can arrange this the result of differentiation in this compact form, m square pi square divided by a square plus n square pi square divided by b square whole square, plus the additional term, that is due to your elastic foundation reaction, that is upward reaction of soil, that is entering here. So, you can see k by d term is present here, and other term that when after conducting this even differentiation second order or fourth order, you will get again your this sign term is coming. Okay. And the sign will be positive, because if negative term appears, another negative terms will appear for differentiation with respect to your y, then the negative multiplied by another negative quantity will be positive. So, this quantity inside the second bracket is positive quantity, and you are getting the deflection surface. Now, you can note here that summation is still present. So, we have to this get rid of the summation term and want to find the value of the constant AMN. Okay. So, multiply both sides by sin m dash pi x by a, sin n dash pi y by b, and integrate in the domain of the plate. What do you understand by domain of the plate? Because it is a rectangular plate, it extends from 0 to a in the length direction and 0 to b in the width direction. So, area of the plate is a across b, a b is the area of the plate. So, in the domain of the plate, if I integrate the equation after multiplying the full equation with another sin m dash pi x by a and sin n dash pi y by b, this term is additionally multiplied here with this original term, so that we can make use of the orthogonality condition. That is the intention for multiplying this and integrating over the domain of the plate. Because of this operation, we can use the orthogonality condition, by which we can get rid of all the terms which are not involving m equal to m dash or n equal to n dash. So, all the terms which contains say sin m pi x into sin m pi x by a will be only this retained here. Other terms, if m is equal to not m dash or n is equal to not n dash, then it will be removed, it will be vanished, because of orthogonality conditions that will be 0. So, right hand side remain as it is, and q x y is our loading function. These loading function may differ. For uniformly distributed load it will be one form, for uniformly varying load it will be in another form, and for concentrated load it will be in another form that I have shown you, that it can be represented by direct delta function. Okay. So, now after doing this operation and using the orthogonality condition, ultimately we get rid of the summation term and we get a m n, that is the most important coefficient of our deflection series. In general term a m n, and m n may vary up to infinity, it is integer, m n and are integer, different combination of m n are possible, say m is equal to 1, n is equal to 1, m is equal to 1, n is equal to 2, m is equal to 1, n is equal to 3, like that different combinations may be possible. So, there will be infinite terms in this series, and we have seen that for deflection only first term is sufficient for this reasonable result, but for bending moment and shear force you have to consider more number of terms. However, we get the accuracy with that series, the series is rapidly converging series. So, after integration we get this a b by 4. Why a b by 4 is there? Because this integration gives you a by 2 when m is equal to m dash, and this integration with respect to y give you b by 2. So, naturally it will be a b by 4, and other terms remain as it is, and the right hand side I have written as 1 by d q m n, where q m n is the all loading function. Okay. Q m n is this function. Okay. So, now one can get the value of a m n. So, a m n is 4 q m n d a b, where d is the flexural rigidity, a and b are the dimension of the plate, and you are getting here this the term which contains the harmonic numbers m and n, and also the dimension of the plate a and b, and it is squared quantity plus k by d, where k is also a positive quantity, d is also a positive quantity. So, this term is always positive inside the bracket. Now, you can note that if k is 0, which actually indicates that there is no elastic foundation. So, just like a simply supported plate that we have studied earlier. So, equation for a m n coincides with the earlier equation. So, this formulation is correct, because we have verified it after putting k is equal to 0, it goes back to our earlier equation, that signifies that plate is not supported. So, q m n is that integration of q x y sin m pi x by a sin n pi y by b dx dy, where the integration is carried out for x with respect to x in the limit 0 to a and with respect to y in the limit 0 to b. For the given loading function or point load, q m n can be determined. Now, once we determine w, that w is here, once we determine w, the series, complete series, after finding the m n, then our other quantity can be found out, other plate quantity can be found out. So, what are the other plate quantities? Bending moment in the x direction, bending moment in the y direction, shear force along the x axis, shear force along the y axis, and S shear along the x axis, S shear along the y axis, and corner reaction R naught, because there are 4 corners. So, at 4 corners we will get lifting up force. Okay. So, with that formulation, that speciality is here, that modulus of subgrade reaction is entering into the expression. Now, let us discuss a case where the plate is carrying the UDL, okay. Plate is carrying the uniformly distributed load. So, in that case the q x y is q naught is a constant quantity, and you will get that q m n is equal to 4 q naught a b m n pi square, where m n is varying from 1, 3, 5 etcetera. Only odd integers have to be considered for this q m n. So, q m n is nothing but actually it can be looked as a Fourier series expansion of the load, and the process is that when the loading function is expressed as a Fourier series, double Fourier series, or here in that case double Fourier series, then we can compare the like terms and find out the coefficient of the unknown coefficient of the deflected surface, then full deflection of the plate can be known. So, A m n, after substituting q m n in the expression for A m n, that is the expression for A m n, we get the A m n as this. So, once the A m n is found, then W x y is A m n into sin m pi x by A sin n pi y by b. So, equation 8 into equation 9 we can get full deflected series. Okay. Right. Maximum deflection will be at the center obviously, because it is symmetrically loaded and the support is also symmetrical. So, at x is equal to a by 2, y is equal to b by 2, it is the center, and we get this W max is equal to this. Okay. So, W max you can see here 16 q naught d pi square, that is the constant term, and under summation that m n terms are there, and k by d, that is the extra term that is appearing here because of elastic foundation reaction. Okay. So, you can see this function can be written as in a convenient form as minus 1 m plus n by 2 minus 1. So, m varies from 1 to 3 5, n is also 1 to 3 5. So, one can find out the convergent of the series with the first few terms, the exact result will be obtained, there will be no difficulty. And let us see here the bending moment in y direction. Okay. So, bending moment in y direction is minus d, curvature in y direction del square w del y square plus mu into del square w del x square. So, it means that Poisson ratio is important for finding the bending moment. So, knowing the deflected curve or deflected surface w, here we call it surface because it is a 2 dimensional problem. So, knowing the deflected surface w, we can find out the derivative, second derivative with respect to x and with respect to y, and then after substituting this in the expression that here expression 16, okay, we can find out the expression for m y. So, expression for m y is given like that, where n and m are integers, and here also again this value is important for m is equal to these odd values of integers are also taken here for calculating the bending moment. Maximum bending moment will be occurring at the center, and therefore, we get the maximum bending moment in two direction by putting x is equal to a by 2 and y is equal to b by 2. Okay. So, let us see another case where the rectangular plate is resting on elastic foundation, but instead of uniformly distributed load it carries a concentrated load. Okay. So, concentrated load is a discrete quantity and therefore, loading function becomes discontinuous. So, because of discontinuity the loading function is not differentiable. So, that is the problem. So, this type of loading case has been handled in my class by limiting process, and also I have illustrated a special mathematical function direct delta, which can be conveniently used to find out the to analyze the plate for discrete loading, that is concentrated load, using the properties of direct delta function. Because of special property of direct delta function, which after integration when this is associated with a function and it is integrated in the limit between any limit in the real line minus infinity to plus infinity, you will get the value of the function at the point where direct delta function is applied or concentrated load is applied. So, by this rule we can find that qmn is qxy sin m pi x by a sin n pi y by b dx dy. But mind one thing, that qxy is not continuous function. Because of discontinuity due to concentrated load, we have to express the qxy in this form. So, qy is xy is expressed as p into the location of the concentrated load is given by the coordinate xi and eta. So, the qxy is represented by p into direct delta function, index is x minus xi, and again direct delta function, the index is y minus eta. So, xi and eta represents the location of the concentrated load, and other variables, say sin m pi x by a and sin n pi y by b are also written here. So, by the property of the direct delta function, we can immediately evaluate the integral without going to lengthy process of limit. So, in that case we have to put x is equal to xi and y is equal to eta, then our integration is found out. So, integration is qmn equal to p sin m pi xi by a sin n pi eta by b. Okay. So, this is the value of qmn. The main thing is here that for any problem of simply supported plate using the Navier's method, we use the deflection series as same as this, okay, in every problem. Only thing is that due to loading condition which are different from problem to problem, we get different values of qmn. That is equivalent to expressing the external loading in terms of Fourier series for different cases. So, we get here qmn is this p sin m pi xi by a sin n pi eta by b. So, once the qmn is obtained, then you can get the amn, as amn contains qmn, it also contains the value of flexural rigidity, dimension of the plate, and for that case, this case the modulus of subgrade reaction is also appearing in the expression, and these are the wave numbers m and n that is appearing due to the assumption of double trigonometric series for the deflection function. So, amn is known. After knowing amn, we can find the deflection of the plate. A complete expression of the deflection of the plate is found out. So, two sine functions are appearing, but these are determined because of location of the concentrated load. Now, in a problem where there are more than one concentrated load, it is possible, because when the bridge deck is subjected to vehicle loading, vehicle has several axles. So, each axle will impose, each axle has two wheels, right and left, and therefore, it will impose the two concentrated load while it is travelling for per axle generally. So, you will get this the multiple axle load, that is multiple concentrated load. So, in that case, the deflection at any point can be found out by the principle of superimposition, because we are only dealing with the linear analysis. Okay. So, once the deflection series is known, then it is possible for us to calculate the bending moment expression. So, bending moment expression mx, the bending moment in x direction, equal to minus d del square w by del x square, that is the curvature along the x direction, plus mu into del square w by del y square. So, that condition we can apply, and the derivative of this function can be now evaluated, because this is a constant, this is also constant, and these are constant. So, we can only we have to deal with this function sin m pi x by a and sin n pi y by b for differentiation purpose. So, once you differentiate and put the value, then you will get the quantity like that. So, this is the complete expression for bending moment. Similarly, bending moment in x direction. Similarly, bending moment for y direction can also be obtained as minus d into del square w by del y square plus mu into del square w by del x square. So, partial derivative of deflection function with respect to y 2 times and partial derivative of deflection function with respect to x 2 times have to be taken and added with in one case multiplied by Poisson ratio. So, that you should remember. So, if it is a steel plate, the Poisson ratio is generally varies from 0.25 to 0.3 or around this, and if it is a concrete slab, then we can take Poisson ratio 0.15 to 0.2. Okay. So, my can be determined, mx as mx is determined, my is also determined, and you can see the difference here. Okay. That is, the curvature is interchanged here only and others are same, and you can see the maximum bending moment occurs at the center, that is obvious. So, x is equal to a by 2 and y is equal to b by 2 is the point where the maximum bending moment occurs, and substituting back this x is equal to a by 2, y is equal to b by 2, here also x is equal to a by 2, y is equal to b by 2, we ultimately get the expression for maximum deflection, expression for maximum bending moment in x direction, expression for maximum bending moment in y direction. So, these are the expressions that are very important, especially for design of deck slab in the bridge, because we are dealing with several concentrated load. UDL is there, you can take it as a superimposed dead load or self weight, but the concentrated load, that is the vehicle imposed load, can be treated by this formulation if the deck slab boundary condition is taken as simply supported. In bridge design handbook, that is generally charts are given for bending moment coefficient in x direction and y direction, and in this chart you will get that bending moment expression is similar to the expression that we have discussed here, that is the curvature in 2 directions are taken into account, but these expressions were in the handbook were obtained using the simply supported boundary condition. So, generally the charts are available in bridge design book and known as Piggot's curve, but it is also written by the authors of bridge design that for continuity of the deck slab one can assume a reduction factor of bending moment as 0.8. That means, simply supported case the bending moment is more. So, a reduction that is the bending moment can be reduced up to 20% due to continuity of the edges. Okay. Now, I shall discuss another problem, that is sometimes it is encountered, and you can see how we have developed the solution. Solution is developed by taking a deflection function or assume a deflection function reasonably that can satisfy the boundary conditions. Okay. Now, here the problem is a triangular plate, but for simplicity I have taken a equilateral triangle. So, each angle of the triangle is 60 degree. So, and we consider the uniform moment distributed along the edges of the triangle are applied, symmetrical moments are applied. The origin is taken at the centroid of the plate. So, that means from the base it is a by 3 and 2a by 3, if the altitude, that is this length, say CD is a, if CD is a, then the centroid is situated at a by 3 from the here from the side AB, and from the apex C it is at a distance of 2a by 3. Okay. So, after getting the CG, now let us formulate the problem. So, we can see that at the boundary, since it is simply supported, again we are taking this plate edge as simply supported, because we are dealing with only simply supported condition. So, in the simply supported case, along the boundary deflection is 0, that is obvious, and another condition is that bending moment is 0. So, bending moment 0 means here say this edge is inclined, it is neither parallel to x axis nor parallel to y axis. So, we have to take the bending moment that is normal to the plate is 0, but here it will be not 0 because the moment m is applied. So, one boundary condition is that along the all edges that deflection is 0, and second boundary condition is that bending moment normal to the edge is equal to m, not 0, because the moment is applied. All right. Now, let us see how we can formulate the problem. Okay. Now, you can see this side say AB, what will be the equation of AB, line AB? Equation of line AB is nothing but x plus a by 3. It is very easily written, the equation of the line x plus a by 3. Equation of the line BC is written in the intercept form, and we can write that x by 2 a by 3 minus y by 2 a by 3 by root 3. This factor root 3, 1 by root 3 is coming because this angle is 30, this angle is 30 degree, and this tan 30. Okay, when we find this intercept BD for that line with the y axis, then BD will be this length into tan 30. Therefore, this condition is appearing. Okay. Now, one important thing you are seeing here, that since the y axis taken downward, so intercept is this, intercept is here this length. So, obviously, it is 2 a by 3 into tan 30. Since it is taken downward positive, therefore, minus sign is coming here, and in the intercept form, say the standard intercept form of the straight line is x by a plus y by b equal to 1. So, here is also the intercept along the x axis is 2 a by 3, that is obvious, OC is 2 a by 3, intercept along y axis is this side, that is 2 a by 3 into tan 30. So, therefore, this is coming, but it is negative because it is in the negative direction, equal to 1. So, 1 I have transferred to the left hand side, equal to 0. All right. Equation of the line AC is similarly written. Now, here the intercept is found as positive. So, positive intercept is found. Now, you can see that the plate equation can be formed or can be composed by taking the equation of the line, because equation of the sides of the triangle, because along the sides, that is along the edges of the triangle, deflection is 0, and when we take the equation of the line or equation of the side of the triangle, that is the side of the plate, as a term of deflected surface, then we can get that along the edges deflection is satisfied. Okay. So, that condition is satisfied by taking W is 0, because along the boundary W is 0, and Mx is equal to M at edges. Now, Mx is equal to M at edge, only it is possible for edge AB, but here this edge is inclined. So, we have to find the normal, the moment along the normal. So, Mn. Okay. Now, let us see the plate equation. Plate equation is del 4 W by del x 4 plus 2 del 4 W divided by del x square into del y square plus del to the power 4 W by del y to the power 4 equal to q by d. Now, since no load is applied here, so right hand side is 0. So, let us see in the next slide. The plate equation indicates that no term in W should be degree higher than the 3, because it is a fourth order equation, and boundary condition W is equal to 0 indicates the expression for W must contain the equations of the boundary lines. So, hence let us try the equation of the line as C1. This is the equation of the line AB. First we have written the equation of the line AB, then equation of the line BC, and the equation of the line AC. So, if you see that equation of the three sides of the triangle are written here and it is multiplied with an unknown constant c. Because of this type of expression, you can see that w equal to 0 is immediately satisfied. There is no doubt about that, because at the boundary this expression has to be 0, this expression has to be 0, this expression has to be 0. Okay. Now, this term can be arranged, because x plus a by 3 I am keeping here, and this can be treated as your say this term can be taken here, say this minus 1 minus y by 2 a 3 root 3, and this term can be taken as it is plus. So, that means a plus b into a minus b, this formula if you apply, you will get a square minus b square. So, I have written like that, and after simplification one can write this expression inside the third bracket as this. Okay. Now, further simplification of this expression will give you w as c 1 x plus a by 3 9 by 4 a square parenthesis x square minus 4 x a divided by 3 plus 4 a square by 9 minus 3 y square. So, this is the expression for deflected surface, provided C 1 is known, because this w is found to satisfy the boundary condition, but still the value of C 1 is not determined, because the second boundary condition on the bending moment is not imposed till now. So, let us see what is the next step. Okay. So, after simplification we have got this, and we can see that if you take this expression of the deflected series and take the derivative, fourth derivative of w with respect to x, then this derivative and again this, you will find these are all 0. So, differential equation is also satisfied, because we have found del 4 w equal to 0 in that case, because no distributed loading is there, no applied loading is there except the edge moment. So, q is 0. So, therefore, differential equation is a homogeneous equation, and by taking the expression of deflected series with this form, it is easily verified that the differential equation is satisfied. So, plate equation is satisfied, that is our inference. Next, w is 0 along the edges, that is we have verified. So, these are the equation of the line. So, naturally it will be 0 at the boundary for the respective edges. So, another boundary condition to be satisfied is moment m n along the normal to this side is m. Now, m n is given as del square w by del n square plus mu into del square w by del t square equal to m. Now, here you can see that derivative is taken not with respect to Cartesian axis x and y, Cartesian coordinates x and y, but it is taken a normal and tangential coordinates n and t, and that transformation from Cartesian derivative to normal derivative or tangential derivative we have covered earlier and given the expression that we will utilize here. Okay. Now, since it is supported along the edges, so naturally this derivative is 0, curvature is 0, and hence we get the condition of bending moment as minus d del square w del n square equal to m. Okay. Now, the bending moment, that is the curvature with respect to the direction n, that is not with respect to direction x or y. So, here the operator, that is the differential operator with respect to n, where alpha is the angle that makes with the x axis, that the normal makes with the x axis. So, that operator is written, and this is nothing but the differentiation of w, that is the deflected surface with respect to your the direction, normal direction. So, this is the derivative and this is the operator. So, we get the second derivative. So, term by term multiplication, and after putting the value of all the quantities w that we have obtained earlier, we get ultimately this expression. This expression can be further simplified and written here in this form. Okay. So, this is our minus m by d, a general expression for minus m by d. Now, we can see what happens along the three sides. Now, along the side A B, if you see this side A B, that is n direction is nothing but x direction, is it not? So, alpha is 0, because alpha is the angle which the normal makes with the x direction. So, naturally here alpha is 0. So, we get this alpha is 0 and x coordinate is minus a by 3. X coordinate along this line is always minus a by 3. So, therefore, the previous equation we can now put alpha is equal to 0 and x is equal to minus a by 3. Okay. Then we can get this form of the equation here, and then we can get the unknown constant C 1. So, unknown constant C 1 can be determined in terms of applied moment m, the side of the plate and flexural rigidity. So, now the constant is known, but we have applied the boundary condition along only one edge A B. Let us now apply the boundary condition along the other edges. So, other edges are your BC edge and AC edge, okay. And that edge makes an angle 60 degree, that is the equilateral triangle. So, this makes an angle of 30 degree with the x axis. Okay. So, now taking the derivative of that function, that is with respect to n, and putting this alpha and x properly for that line, say for BC, we can get this expression, and here this expression can be rearranged taking this 2a as common, and it can be rearranged like that, from where we can get this, because this quantity is again minus 1. Okay, this quantity is minus 1 from the equation of the line. So, it will be minus 1 minus 2. So, it is coming as 9 C 1 divided by 4 a square into 2a into minus 2. So, it is equal to minus 9 C 1 by d. So, hence C 1 equal to m a by 9 d. So, same value is obtained again applying the boundary condition, moment condition along the edge BC. Okay. If moment boundary along AC is imposed, then also we get C is equal to m a by 9 d. So, after substituting now C 1 or the constant associated with the deflected series, we now get this W is equal to 9 C divided by 4 a square, parenthesis x cube minus 3 x square minus a x square plus y square plus 4 by 27 a cube. This is the deflected series, and putting the value of C, as C is found as m a by 9 d. So, after putting the value of C, we get the W is this in terms of all known parameters. M is also known, as condition is known, as bending moment is known, size of the plate is known, flexural rigidity which contains the thickness of the plate, and material properties are also known. Okay. Now, let us see what will be the variation of bending moment along CD. So, we will see the variation of bending moment along this line, because bending moment along the edges are known. So, let us see, if we calculate the bending moment along CD, that is along the x direction, that is the derivative, along the y direction, that is the curvature. Okay. So, taking the second derivative of this expression with respect to x and second derivative of this expression with respect to y, we get these two equation, del square w by del x square equal to m by 4 a d bracket 6 x minus 2 a, and another case del square w by del y square equal to m divided by 4 a d bracket minus 6 a minus 2 a. Okay. So, bending moment can be written conveniently like that. Of course, the twisting moment is also found out. So, cross derivative is calculated by taking the differential coefficient of w with respect to x and with respect to y. Now, after substituting this value, you can see the bending moment along the x direction is this, and bending moment along y direction is this. Okay. You can see that both are varying with x, and this twisting moment along this direction is a function of y. So, if I plot this, the variation of m x along the CD, we get this shape, okay. and variation of my along the CD, we get this shape. The value at the extreme edge are this quantity. At this extreme edge, the two values are equal. So, m by 2 equal to minus 1 by 3 mu, and here you will get m by 2 3 into minus mu, and here you will get mu into m. But since the torsional moment or twisting moment does not contain any x, so when we plotted the variation of mxy along the x axis, it represents a straight line. Okay. So, that is the problem that I have discussed, the special cases where the triangular plate is subjected to edge moment. The main philosophy of solution of this type of problem is to take the deflected surface as a function of x and y in the form of polynomial, such that it contains the equation of the line. So, equation of the line when it is associated in the deflected surface, it obviously satisfies the deflected boundary condition at the edges. Another condition, when it is imposed, this gives the coefficient, unknown coefficient associated with the deflected function. Then we get the complete expression for deflection, and then we go forward to calculate the other quantities. Okay. Now, lastly, let us discuss some two problems. One is rectangular plate simply supported along the edges is subjected to sinusoidally varying load. Let us see, this is a very interesting case and easy also. Analyze the plate taking first term of Navier series. Now, for simplicity, let us illustrate it with the only one term of the Navier series, that is m is equal to 1 and n is equal to 1. So, first problem will be solved like that, and second problem we have taken a rectangular plate simply supported along the edges and is subjected to hydrostatic pressure. Find the general expression for the deflected surface. So, these two problems can be solved by Navier's method, that is why I have selected. So, first problem, some important steps I am giving. The procedures are same, whatever load is there, but only thing is that qmn, that is the loading function, have to be now changed because of a different type of loading. Since loading is this, so q11 is nothing but this is the loading and multiplied by sin pi x by a sin pi y by b. Here m is equal to 1 and n is equal to 1 is taken. So, therefore, no m and n is appearing in this expression. Now, that integration can be done very conveniently, because sin square pi x by a dx will be a by 2 and sin square pi y by b will be b by 2. So, net result will be q naught a b by 4. Once you find the q 11, then you can find a 11 as 4 q 11 d a b pi to the power 4, and here actually m square by a square was there, but m is 1. So, 1 by a square plus n square by b square were there, but since n is 1. So, 1 by b square and whole square. So, this is the expression for a 11. After knowing a 11, we can find the complete deflected series. So, hence the deflected surface is given by this function. So, this solves the first question. Let us come to the second question. Second question is a rectangular plate again, the length is a and side is b, and it is simply supported along the edges, but it is subjected to uniformly varying load. That is, this type of load is hydrostatic pressure, and it is very common, especially when the plate is used to resist the earth pressure or resist the say water pressure in a sluice gate used in flood control works. Then the pressure will vary uniformly linearly from base to the top, and the maximum, and it will the pressure will be linearly varying with the depth or distance. So, therefore, the maximum pressure that you will get at the one extreme edge, and here it is 0. So, this pressure is q naught, and some important hints I am giving you. The deflected the loading function is expressed as q naught by a divided by x, because the variation is only along the x axis. At any section along the y axis, you will find the same intensity of the load. So, y is not coming in this expression. So, therefore, qmn is written as a integral 0 to a and also 0 to b q x y sin m pi x by a sin n pi y by b dx dy. So, therefore, this integral is carried out, and here you will get this constant term is taken out, and this integral is done with the rule of integration by parts, and this is the integration of sign integration, okay, sin n pi y by b dy. So, two integration when it is carried out, that integration by parts, the first integral is this, and after putting limit you will get q m n is minus 2 q naught cos m pi divided by m n pi square for all integers m n n being odd. So, once you get q m n, then you can find a m n again for the value of odd integers. So, therefore, after getting your value of a m n, you can get the deflected series w x y. Now, here because of this uniformly varying load, you will not find the deflection exactly at the center. Maximum deflection will occur along the line b by 2, this at the center of the plate, but this the x coordinate will be different. So, x coordinate has to be found by differentiating or making the slope to be 0, because at the point of maximum deflection you will get slope 0. So, finding this location x where the slope vanishes along the x direction, you will find the and put in the deflected surface again the value of x, y is equal to b by 2, and value of x has to be found after making the slope to be 0, you will get the magnitude of the maximum deflection. Okay. Similarly, you can find the magnitude of the maximum bending moment and in the x and y direction. Okay. So, what we have done today's class is we have illustrated the problem of plate on elastic foundation. Then I have discussed a special problem where a triangular shaped plate is taken, and the plate is equilateral and subjected to moment along the edges. This moment, of course, the magnitude is taken equal and it is symmetrical, that it is trying to sag the plate. So, under the action of this edge moment, we have found the deflected surface of the triangular plate, and from that we have found the expression for bending moment and twisting moment. Then we have taken two problems of that can be solved applying Navier's method that we have learned so far in our module 2, and applying Navier's method that I have shown, that procedure is same, only you have to get the value of q m n for each case of loading, different types of loading. The uniformly distributed load is more common, but any other load appears on the plate or acting on the plate, then you have to find q m n based on the loading function. So, that I have discussed, and two problems of practical importance, that is a sinusoidally varying load on the plate and a hydrostatic pressure acting on the plate have been discussed and solution have been found out. Okay. So, thank you very much.